Okay, we're going to quickly look at section 4.9 where we're undoing what we did. And we have this idea of the antiderivative, which is a function, big f of x, will be an antiderivative of another function, which we call little f of x, on the interval, if when you take the derivative of the big function, you get the little function. So you're going to be saying to yourself, what is the derivative, what function has the function that I'm looking at as the derivative? And that will be called the antiderivative. So of course we looked at the classic example, like if you have x squared, what function did you take the derivative of to get x squared? Well, obviously x cubed would work, because when you use the power rule you do 3 minus 1, which would be 2, but then you got to take care of the fact that normally if you had just x cubed, the derivative of that would be 3x squared, and you've got to get rid of that 3 in front, so that's why we put that 1/3 there. And you'll see that you can take the derivative of this function and it will just be x squared, so these are always self-checking. But the thing is that it could be that you could add a number to this, like if you added a constant, like 1/3 x cubed plus 5, the derivative of that would also be x squared, because whenever you have any number that you add to this function is still going to have a derivative of 0. So what you really have is a family of functions who are at different places along the y-axis but have the same shape, and they all have as their derivative the function f of x that you're given. So that takes us to this idea of the general antiderivative. Let f of x be an antiderivative of little f of x on AB. Then every other antiderivative of on that same interval is of the form f of x plus c for some constant c. All right, so let's look. This is number 4 on your homework. You're asked to find the general antiderivative of, and then check your answer by differentiating. And it's f of x equals 9x plus 15x to the negative 2. Now, I'm going to give you a rule, like a little power rule, to handle this in the future, but for right now we're just going to use our brains. Okay, we need, our new function is going to be big f of x, and it's going to be the antiderivative. So you think to yourself, all right, well, what would you have to take, what function would you take the derivative of where you would get 9x? Well, the constant always is just going to tag along, so you can just write your 9 there. And let's think about x. To get just x in your derivative, you would need to have an x squared originally. So you know the 2 would come in front, right? But that would be 9 times 2, which would be bad because we just want 9x. So if we divide by 2, then when we take the derivative of 9x squared divided by 2, it does in fact equal 9x. Okay, so that part's good. Now let's try this one. Again, the 15 is just going to tag along. Let's think about what would your exponent be if the derivative was negative 2. Well, remember when you're doing a derivative, you subtract 1 from the exponent. So to get negative 2, you'd have to have a negative 1 already there. So this would be x to the negative 1. But when you take the derivative of this, you would get the negative 1 in front, x to negative 1 minus 1, which would be negative 2, but you'd have a negative here. So we need to divide by negative 1. If we do that, then when we take the derivative of this function, we will in fact get just 15x to the negative 2. And then we remember that we could add any constant to that, and it wouldn't affect the derivative because the derivative of the constant is 0. So our big function, 9x squared, our original function, our antiderivative, is 9x squared minus 15x to the negative 1 plus c. I got that minus just from distributing there. And then we can check by doing f prime, big F prime of x, all right? Well, the 2 would come in front. You'll have 9 times 2x squared divided by 2. So those are going to cancel. And then the negative 1 comes in front. Negative 1, 15 times negative 1, x to the negative 1 minus 1, which is negative 2. And then plus the derivative of the constant is 0. So you do in fact get 9x squared, and the negatives cancel, plus 15x to the negative 2 Oh, sorry, I didn't change that. It's just the 2 comes in front and the 2 minus 1. So you get 9x plus 15x to the negative 2. Okay, so they check. So this is this process of finding an antiderivative is called integration. And antiderivative is called integration. And we have a new notation. It's kind of exciting because you probably have seen this before, but maybe you didn't know what it meant. And it's for what we call the indefinite interval. Later in the semester, we'll learn about the definite interval, but right now it's just the indefinite interval. And it is, we have this notation, antiderivative is this little s, but it's kind of like a long skinny f, and we think antiderivative of our little f of x dx is equal to big f of x plus c. And what that means is that if we take big f of x, the derivative, we will get little f of x. And we have, we say that this big f of x plus c is the general antiderivative, or sometimes we hear the word indefinite interval. Indefinite interval. So those are some new words for you. And this little function, little f of x right here, he's called the integrand, the one who is being integrated. Okay, and the symbol dx, this is your differential. It's kind of what you're integrating with respect to. You'll hear me a lot say that. And this number right here, the c, is called the constant of integration. Now I promised this video wouldn't be very long, so I'm going to give you some rules for intervals, some basic rules which probably should feel pretty good to you, and then I'm just going to work a few problems. The first one is Theorem 2 in your textbook. It's the power rule. And it's the pattern that you probably were recognizing before. If you want to integrate x to the n dx, what you do is, remember when it was x squared, we wanted it to be x cubed, so we added 1 to the exponent. So it's x to the n plus 1 divided by that same thing, n plus 1, and then plus c, as long as n is not equal to negative 1. Okay? Now, here's our rule. So we do x to the n plus 1 divided by n plus 1. So let's apply it. Let's do a couple examples from your textbook. Here's number 17 in your homework. The antiderivative of z to the negative 4/5 minus z to the 2/3 plus z to the 5/4, and then with respect to z, so dz. All right? So you're just going to apply the power rule to each of these terms. One thing that students do wrong is they forget to get rid of this integral sign. Once you apply the power rule, the integral sign no longer appears. So we're going to have some fractions here. It's going to be z to the negative 4/5 plus 1 divided by negative 4/5 plus 1 minus z to the 2/3 plus 1 divided by 2/3 plus 1 plus z to the 5/4 plus 1 divided by 5/4 plus 1, and then plus c. So you want to clean this up a little bit. 1 can be thought of as 5/5, so negative 4/5 and 5/5 is just 1/5. So you're going to have z to the 1/5 divided by 1/5 minus 1 here could be thought of as 3/3, so that's going to be z to the 2/3 plus 3/3 is 5/3 divided by 5/3. And then here you can think of that as 4/4, so this is z to the 9/4 divided by 9/4 plus c. And a lot of times I don't show this many steps, but of course we would flip this fraction in the denominator. So this is 5z to the 1/5 minus 5/3 z to the 5/3 plus 4/9 z to the 9/4 plus c. And you should be able to convince yourself that this is going to check. You can check by differentiating your answer. And you should get the integrand answer. So this, what you get is your big f of x, and if you then take the derivative of that, you should come back to the integrand, which was the little f of x. But I'm going to, in the interest of time, let you do that on your own. Let's try another one. This is number 24 in your homework. The antiderivative of 12 minus z divided by the square root of z dz. Now you'll remember that I talk about whenever you divide by a monomial, you definitely want to split it up, and this is especially important in these types of problems. So you want to think of this first before you want to simplify this a little bit. It's 12 over the square root of z minus z over the square root of z, right? But and I'm just going to write z, the square root of z, as z to the 1/2, because that's going to be a better way to think of it. And then I'm still simplifying. I haven't done the antiderivative yet, so I'm going to do my symbol, the antiderivative symbol, the integral symbol, and this will be 12z to the negative 1/2 minus, all right, z to the 1 over z to the 1/2. You subtract the exponent, so that's going to be z to the 1/2 dz. Okay, now I'm ready to use the power rule. So I take the derivative by adding 1 to the exponent and putting it over it. And no, I will no longer write this little symbol, the little integral symbol. So this is going to be 12z to the negative 1/2 plus 1 divided by negative 1/2 plus 1 minus z to the 1/2 plus 1 divided by 1/2 plus 1. And then, of course, you have your plus c. Then we'll just clean this up. So this is 12z, negative 1/2 plus 1 is 1/2. This is divided by 1/2. And then this is minus z to the 3/2 over 1/2 plus 1, again, 3/2 plus c. And then in its cleanest form, you'll flip these fractions on the bottom. So this is 24z to the 1/2 minus 2/3 z to the 3/2 plus c. And again, you can check your answer. If you take the derivative of your answer, you should get back to the integrand, which really you'll get it in that form. All right. There's another theorem, and if you want to find the antiderivative of 1 over x, so the antiderivative of 1 over x dx, you can't use the power rule because that's like x to the negative 1. If you added 1 to that, it would just be 0. But if you think about it, you know the function that has 1 over x as its derivative. Think for a second, what function do you take the derivative of and you get 1 over x? Well, that's the logarithm. Now, you're describing, it is the logarithm of x plus some c. Now, the only problem here is that you can't take the log of a negative number. So your function, your general antiderivative, you have to make sure that you take that the x that you're taking the log of is positive. So we put our answer in absolute values. Now, there is a proof of this theorem in your textbook. So if you feel uncomfortable about the absolute value, let me just look at this. On page, let's see, right about on page 276, you'll see why you have to deal with that absolute value. But I just want to apply it here, just remembering that the antiderivative of 1 over x is ln absolute value of x plus c. Now I wanted to give some others. I bet you know this one, the antiderivative of e to the x dx. Oh, well, you remember that the derivative of e to the x is e to the x, so the antiderivative is also easy, right? It's just going to be e to the x dx. Now, what about if it was more exciting? What if it was the antiderivative of e to the, say, kx plus b dx, where k and b are constants? For constants, numbers, k and b. Well, that's, and obviously k can't be 0 because that's kind of silly. Well, that is just going to be 1 over k e to the kx plus b plus c. And you can probably see why, because if you take the derivative of this 1 over k e to the kx plus b, it'll just be e to the kx plus b times the derivative of kx plus b, which is k. So you have to get rid of that, so that's why you have the 1 over k there. All right, so this allows us to do some more problems now that we have the antiderivative of 1 over x, the antiderivative of e to the x, and e to the kx. We can do a couple more problems from your homework. Here's number 36. It says find the antiderivative of 4 over x minus e to the x dx. Now, these constants, these numbers, they're just going to tag along in your answer. So if you want, you can split this up and think of this as 4 times the antiderivative of 1 over x minus, and then put a dx, minus the antiderivative of e to the x dx. So it's kind of like, it's like a distributive property, but not really. And I kind of factored that 4 out. But then right away, you know the antiderivative of 1 over x dx. That's ln x. This is going to be ln of absolute value of x, minus the antiderivative of e to the x is just e to the x. Excuse me. And then plus c. So you just have to memorize those antiderivatives, and the more you practice, the better you'll get at it. All right, so here's number 39 from your homework. The antiderivative of 8x minus 4e to the 5 minus 2x dx. So again, you can split this up and think of them separately. And the constants can come out in front so they don't stress you out. So 8 antiderivative of x minus 4 antiderivative e to the 5 minus 2x. Oh, and each of these has a dx, just from a notation standpoint. All right, well, this one we can just use the power rule on. So it's going to be 8 times x squared over 2, because you add 1 to the exponent, put it over it, minus 4. Okay, now the rule for e to the 5x minus 2 is you just going to have e to the 5 minus 2x. But you're going to divide by the constant in front of the x, which in this case is negative 2. Because remember, the formula here is 1 over k e to the kx plus b, where the k is the coefficient in front of the x. So that's why I divided by the negative 2 there, because that's like my k. All right, and then we always have to remember our plus c, because it's a family of antiderivatives. Okay, you can simplify this. 2 goes into 8 4 times is 4x squared. And then plus 2 goes into 4 2 times 2e to the 5 minus 2x plus c. Now, if you take the derivative of this, which you could do very quickly, you should see that you do in fact get the integrand. Remember, this is your big f of x. This is your little f of x. So note, the derivative of big f of x does equal, well, I can do it real quick, 8x plus, let's see, the 2 is going to tag along, and then it's e to the 5 minus 2x times the derivative of that, which is negative 2, and the derivative of constant is 0. So that's 8x minus 4e to the 5 minus 2x, which is exactly the integrand, the little f of x that we had inside the integral symbol. Okay? So these are kind of fun. You just want to take a lot of practice to work them. All right, so let's do a few more rules. We haven't done any trig functions, but we can probably think those through pretty quickly. What function would have as its derivative the sine of x? Well, that would be negative cosine x plus c. If you take the derivative of cosine x, you get negative sine x. So you need the opposite. You need the negative here if you're just going to find the integral or the antiderivative of sine x. All right, well, what about antiderivative of cosine x dx? What function has as its derivative cosine x? That's sine x. And then, of course, the antiderivative of tangent, tangent isn't going to have one. But we do know the derivative of tangent is secant squared x, one that we know yet, that we're going to cover in this lesson. Okay, the antiderivative of secant squared x dx is going to be tangent x plus c. All right, so let's see. We know that the derivative of the secant is secant x tangent x. So that means we know that the integral of secant x tangent x dx will be equal to just secant x plus c. Because, you know, you have to think about what derivatives you know. Let's see, what else do we know? Well, cosecant squared x dx, the function that has that as its derivative is negative cotangent x plus c. So you can find the function that has as its derivative cosine squared x, that is the negative cotangent. And then finally, remember that the derivative of the cosecant is negative cosecant x cotangent x, so you can go the other way, and we'll think of it positive. If we antidifferentiate cosecant x cotangent x, we get negative cosecant x plus. Okay, now if we wanted to think about it a little bit more carefully, say we had an antiderivative of sine a constant k times x plus b dx. What would the function that has that as its derivative look like? Well, you can probably convince yourself of this, that you're going to have to do something with that k, because if you take the derivative, say you were just dealing with the derivative of this, well, it would be cosine kx plus b times k. So if you want to handle it, you're going to have to divide by that k. Now, we know the antiderivative of sine is negative cosine, so we'll have negative 1 over k cosine kx plus b plus c, as long as k is not equal to 0, which would be silly anyway. And the antiderivative of the cosine of kx plus b, what function has as its derivative cosine kx plus b? Well, that's going to be sine kx plus b, but you have to handle that constant in front of the x by doing the 1 over k, because when you do the chain rule you get that k, so you've got to make sure that goes away. So that's your antiderivative of a function cosine kx plus b. So we can do some more examples from your homework. Here's number 28. The antiderivative of theta plus secant squared theta d theta. All right, so what I want you to do is think of these separately. So this is the antiderivative of theta d theta plus the antiderivative of secant squared theta d theta. Well, the antiderivative of theta, that's just like the antiderivative of x. That's just the power rule. You just add 1 to the exponent, so it's going to be theta squared divided by the exponent plus 1, so 2. See, if you take the derivative of that, you will just get theta. Plus, okay, we just learned the antiderivative of secant squared is tangent x, or in this case, tangent theta, and then plus c. Remember, you can always check. If you take the derivative of this is big F of x. If you take the derivative of that, you will get your integrand if you did it correctly. Okay, now we'll look at number 35 in your homework. You're asked to find the antiderivative of cosine 3 theta minus 1/2 secant squared theta divided by 4, and then all of that d theta. Okay, and so I remind you to don't worry about these constants, kind of let them tag along, and you can separate these integrals. So the integral of cosine 3 theta d theta minus, I'm put the 1/2 in front, the integral of secant squared theta over 4, and then d theta. Okay, well, the integral of the cosine is the sine, but since you have this 3 theta here, you have to sort of unchain rule it. So that's going to be like 1 over k. So this is going to be 1 over 3 sine 3 theta. And just in your head real quickly, take that derivative. Does it make cosine 3 theta? Yes, because the derivative of sine is cosine. You would cosine 3 theta, but then you'd have to do times the derivative of the inside, which is 3. So to get rid of that 3, you have to divide by the 1/3. All right, now minus 1/2. Right, what function has its derivative secant squared? That's the tangent. So you're going to do tangent theta over 4, but you're going to have to handle that 1/4 there, which means you're going to need to divide by 1/4. So you can divide by 1/4 that way, or which is the same as multiplying by 4. And then, of course, you have your plus c. So this cleans up to be 1/3 sine 3 theta minus, so the multiplying by 4 is the same as dividing by 1/4. So this is 1/2 of 4, which is 2 tangent theta over 4 plus c. And so you might want to practice, take the derivative of that and see that it does work. See, the derivative of tangent theta over 4 is going to be secant squared theta over 4 times the derivative of theta over 4, which is 1/4. When you have that 2 in front, the 1/4 and the 2 makes 1/2, which is what you started with there, that 1/2. That's where that 1/2 comes from. So dealing with those fractions can be a little bit confusing. Okay, well, sometimes you have what's called a differential equation, which is where you can actually compute the c value if you're given some what we call initial conditions. So let's take a few notes on that first. So what we do is we can think of an antiderivative as a solution to the differential equation. So isn't this exciting? That's another math class you can take called DiffEq. So we have an equation where dy dx is equal to f of x. So that is what the antiderivative is. So it says, in general, a differential equation is an equation relating an unknown function and its derivative. And sometimes you can find the specific equation if you're given an initial condition. The specific equation, if given an initial condition, some original value. So basically this is how to find the c when you do the antiderivative. It only works when you're given some extra information to try and figure it out. So here is a homework question that'll kind of help you. This is number 56. You're asked to solve the differential equation, dy dz is equal to the sine of 2z when y at pi over 4 is equal to 4. All right? So what you want to do is you kind of like, it's almost like you you kind of cross multiply here, but it's not exactly what you're doing, but you can kind of think of this as saying to yourself, okay, well, dy is equal to sine 2z dz. And if I were to integrate both sides, then the integral of dy is just going to be y, you know? And the integral of sine 2z dz, well, the function that has as its derivative sine is negative cosine, but when I have this 2, because I have this 2 in front of the z, I'm going to have to put a 1/2 in front of my antiderivative. So this is going to be y equals negative 1/2 cosine 2z plus c. But here's where something exciting comes into play, and that is that we were told that y at pi over 4 is equal to 4. So this means that when z equals pi over 4, y equals 4. So we can plug that in and find c. All right, so how do we do that? Oops, my page, I lost my page, sorry. I really lost it. Where'd it go? There it is. Okay, so y is equal to 4, so I'm going to put a 4 in for y, and then I have negative 1/2 cosine 2, and instead of z, I'm going to put pi over 4, and then plus c. So I just have to solve for that. So this isn't going to be too bad. So this is 4 equals negative 1/2 the cosine of pi over 4. 2 times pi over 4 is pi over 2 plus c. Now this doesn't always happen, But this is kind of fun here because the cosine of pi over 2 is 0. So this is 4 equals negative 1/2 times 0 plus c. So 4 is equal to your c. So now you have found the exact equation that has as its derivative the sine of 2z. And that is our equation that we found, our antiderivative, negative 1/2 cosine 2z plus the c, which is 4. So this function that you found will have a derivative of the sine 2z, but then it also has it has a criterion, it meets the requirement that when you plug in pi over 4, you do get, in fact, 4. So that's kind of just an example of what we call an initial condition, or a differential equation. So the last question that we're going to look at is number 71. This is a word problem, but it's dealing with these differential equations. It says a particle located at the origin at t equals 1, 1 second, moves along the x-axis with velocity v of t is equal to 6t squared minus t meters per second. And then it says, state the differential equation with the initial condition satisfied by the position s of t of the particle, and find s of t. Okay, so what we know is, so let me write that. So it says state the differential equation with initial condition satisfied by the position of the particle, which is s of t, and find it. Go ahead and find s of t. Okay, now we know that the derivative of position is velocity. So we know that ds dt is equal to v of t. The derivative of position, remember position is your is s. Okay, now they gave us an initial condition. It's kind of hard to figure out, but it says it's located at the origin at t equals 1 second. So that means that the position function s at 1 second is going to be equal to the origin, because you're located at the origin, so it's equal to 0. All right, so this is my initial condition. This is my differential equation. And so I know what v of t is because they gave it to me. They told me it was 6t squared minus t. So I can integrate this equation and find the antiderivative and then plug in my initial condition to figure out what c is. All right, so if I antidifferentiate this, dt, I'll just use the power rule, so I'm just going to antidifferentiate. I'm going to figure out what function has that as a derivative. Right, well, the 6 just tags along, and that you add 1 to the exponent, so t to the 2 plus 1 is 3, and divide by it, so that's 3, minus, all right, t, you add 1 to the exponent, so that's 2, divided by it was 2, and then plus c. So s of t is equal to, let's see, this cleans up to be 2t cubed minus t squared over 2 plus c. So that's your general antiderivative. But you have enough information to figure out what c is, and that's because you know that s of 1 is equal to 0. So when t equals 1, s equals 0. So you can plug that in. So s of 1 is equal to 0. So 2 times 1 cubed minus 1 squared over 2 plus c. So you put 0 in, you get 0 for s when you plug 1 in for t. So now I can just solve this. Is pretty easy. 0 equals 2 minus a half plus c. And so let's see, 0 is equal to 2 minus a half is 3 halves plus c. So c is equal to negative 3 halves. So I have now my specific equation is back at this s of t, but I know what c is now. So s of t is equal to 2t cubed minus t squared over 2 minus 3 halves. So now you can tell your parents that you learned about differential equations today in calculus. Very exciting stuff. All right, have fun doing the homework.